Uranium is the most valuable and dangerous element that humanity can extract from the Earth. Just a piece the size of a walnut could generate enough energy to power the entire city of New York for more than a full day. But how is it possible for a simple rock to have so much power? Why is it so dangerous? Well, today we will travel to Kazakhstan, home to the world's largest uranium processing plant, where every day more than 500 tons of this rock are transformed into the most potent energy that exists. So get ready, because today we are going to discover how the most powerful material on the planet is produced on a massive scale. Let's begin. Step 1. Extraction of natural uranium. It all starts hundreds of meters underground, where one of the rarest and most dangerous minerals on the planet is hidden, uraninite. To the naked eye, it looks like just an insignificant black rock, but inside it holds the most coveted and powerful ingredient in the nuclear industry, uranium-235. Obtaining it is one of the most extreme and complex challenges in the entire mining industry. Within each rock, this material is present in minimal quantities. Less than 1% of each stone is actually useful. This means that to get just 1 kilogram of usable uranium, more than 500 tons of ore must be processed. And don't think that's insignificant. Just 1 kilogram of uranium contains enough energy to keep more than 200,000 homes running for a full year. To extract it, huge excavators and hydraulic shovels remove tons of rock, while giant drills open tunnels that go deep in search of this mineral. The entire process is carried out under strict safety measures, because although in rock form it is not as lethal as in a reactor, the uranium it contains is still extremely radioactive. If not handled correctly, it could contaminate the area, put workers at serious risk, and even cause a catastrophe. Once extracted, the tons of rock are loaded into giant mining trucks and transported to processing plants, where their transformation into nuclear energy begins. Step 2. Refining and creation of yellowcake. When the trucks arrive at the plant, the tons of radioactive rock are unloaded directly into enormous steel hoppers. From there, the material travels on conveyor belts to the pre-treatment area, where vibrating sieves and high-pressure water jets remove all useless debris such as dirt, mud, and any superficial impurities. What remains is pure rock loaded with uranium, which is sent to gigantic industrial crushers. There, their steel jaws pulverize the stones, turning them into a fine, dark, highly radioactive powder. But the real secret is here. That powder is submerged in chemical tanks, with acidic solutions designed to dissolve all the leftover minerals and isolate only the most valuable component. The result is a dense, bright yellow paste, known as yellowcake. To the naked eye, it is similar to cornmeal and seems harmless, but it contains up to 80% pure uranium. Therefore, any minor failure in its handling can cost lives and cause irreversible radioactive contamination. Under strict safety controls, the yellowcake is dried, packaged in sealed drums, and sent to the next stage of its transformation. Step 3. Converting uranium to gas. The kilos of yellowcake arrive at the plant in large sealed drums under maximum security. Here, the mission is to transform that yellow powder into a gaseous compound that can be enriched and converted into a real power source, uranium hexafluoride. It might sound like a chemistry lesson, but this is where one of the most delicate phases of the entire process begins. First, the yellowcake is introduced into enormous, ultra-resistant stainless steel chemical reactors. Using special solutions, it's washed and filtered to make it as pure as possible. Then, the purified uranium is mixed with hydrofluoric acid and heated to temperatures of up to 50 degrees Celsius, causing a chemical reaction that transforms it into uranium hexafluoride. This compound is unique. At room temperature, it's a solid, inert substance. But when heated, it becomes one of the most dangerous gases in the world. Once generated, the uranium hexafluoride is stored in armored steel cylinders designed to withstand impacts, corrosion, and leaks. This is nothing like the typical fluorescent green rods you see in shows like The Simpsons. We're talking about a substance so dangerous that direct human contact is practically impossible, or the consequences would be fatal. With the material ready in its gaseous form, we move to the most critical step of the process. Step 4. Uranium enrichment. We've arrived at the most critical and delicate stage of the entire process. At this point, the uranium hexafluoride is made up of two types of uranium: uranium-238, which isn't useful for generating energy, and uranium-235, the only one capable of sustaining an energetic reaction. The goal is clear: separate them and keep the uranium-235. To achieve this, the uranium hexafluoride, now in gaseous form, is injected into enormous industrial centrifuges. These are literally like giant washing machines that spin at more than 50,000 revolutions per minute inside vacuum chambers. At such extreme speeds, even a minimal weight difference the size of a few specks of dust can destabilize the machine and cause it to self-destruct in a matter of seconds. As it spins, the centrifugal force pushes the heavier uranium-238 to the outside, while the lighter uranium-235 becomes concentrated in the center. The enriched gas is extracted and passed to the next centrifuge, and so on, in long chains called enrichment cascades. Hundreds or even thousands of machines work in series, gradually refining the content until the uranium reaches the necessary purity for its use. In the end, uranium-235 is obtained with the exact percentage needed to be used as nuclear fuel for commercial reactors, which is around 5%. The rest, depleted uranium, is stored for other industrial uses, such as high-density shielding or counterweights. With the enriched uranium ready, we have the most important part. Now, we just need to give it a physical form and transform it into the fuel that will power a reactor capable of moving entire cities. Step 5. Manufacturing fuel pellets. With the uranium now enriched, it's time to give it a physical form so it can fuel a reactor and power an entire nuclear plant. The enriched hexafluoride gas is introduced into special reactors and subjected to a new chemical process that converts it back into a very fine powder, but now much purer and more valuable than at any previous stage. This powder is taken to industrial presses that compact it into small, cylindrical pieces about the size of a 1 centimeter diameter coin. At a glance, they seem harmless, but each one holds an energetic power capable of moving trains, ships, or entire cities when released in a reactor. After molding, the pellets are placed in special furnaces where they are baked at temperatures exceeding 1,000 degrees Celsius. This baking process turns them into an extremely hard and resistant ceramic material, capable of withstanding the intense radiation and heat of a reactor core for years without decomposing. Once cooled, each pellet undergoes rigorous quality control: X-rays to detect microscopic internal cracks, laser scanners that precisely measure dimensions, and chemical analyses that ensure there are no impurities that could alter the nuclear reaction. At the end of this step, we have thousands of small nuclear batteries ready to be packaged and sent to one of their final processes. Step 6. Assembling fuel rods and modules. The thousands of ceramic uranium pellets arrive at the assembly area, where precision is everything. Here, automated machinery and industrial robots insert each pellet into long, thin tubes made from a zirconium alloy, one of the most resistant metals on the planet. It can withstand extreme temperatures and allows neutrons to pass through without absorbing them. Each tube, known as a fuel rod, can hold up to 400 pellets stacked with millimeter precision. This is enough to keep a large military base fully operational for more than a year. Once filled, the ends are sealed with laser welding, creating a hermetic seal capable of withstanding the brutal conditions inside a nuclear reactor. The finished rods are then grouped into structures called fuel assemblies, large metal frames that hold dozens of perfectly aligned rods. Each assembly can weigh up to 500 kilograms and requires more than 100,000 weld points, all inspected with ultrasound to guarantee their integrity. Not even the smallest hole can be overlooked here. Before leaving the plant, the assemblies undergo vibration, pressure, and structural analyses that simulate the extreme conditions of a reactor. If they pass all the tests, these gigantic nuclear cartridges are ready for their final destination: to power the heart of a plant capable of providing electricity to an entire city for years. Step 7. Final inspection and shipment to the reactor. With the assemblies complete, the last and most demanding phase begins: the final inspection. Each piece goes through a series of extreme tests that leave no room for error. High-precision scales verify that the uranium's weight is accurate to the gram. Ultrasonic scanners check every weld for invisible cracks, and thermal cameras simulate the reactor's heat to ensure there will be no deformations. Any failure, no matter how small, could cause a serious incident inside the reactor and lead to a catastrophe. When an assembly passes all controls, it is packaged in armored containers and loaded onto specialized transport vehicles. These enormous trucks travel under escort, following strictly planned routes, as they carry the energetic heart that will start a nuclear power plant. Upon arrival at its destination, the assemblies are placed into the reactor core. Once installed, they will begin to release the most powerful energy on the planet, which will be transformed into electricity capable of powering entire cities and even countries for years. But not all enriched uranium ends up in power plants. A portion in the wrong hands can be used to manufacture one of the most destructive weapons ever created, the nuclear bomb. To conclude, tell us, did you imagine this entire process? Do you think nuclear energy is a step forward, or is it too great a risk? Leave us your answer in the comments. And if you like this video, don't forget to like it, subscribe, and hit the bell to not miss the next factory tour.